Hello. This week we're going to be talking about waves, sound, and music. And so waves are a very general subject. Waves are everywhere. Okay? And if the beautiful thing about waves is that if you know one wave, you understand one wave, you actually understand them all because they all have the same properties. They all do the same things. So, and then the easy wave that you can easily deal with are sound waves. Okay, they're very familiar. They're microphones and speakers and so on. So sound waves is easy wave to understand and to play with. And then that naturally leads into musical instruments. And so at the end, maybe we'll contemplate possibly in a school classroom, you can actually do some interesting things with music and sound. So now, practical things about waves, practical things about sound and waves in general, but also apart from hearing and seeing, of course, which we do with waves, sound waves and light waves, we hear and see. There's the Doppler effect, Doppler Radar. Police cars have Doppler Radar. They know exactly how fast you're traveling by sending electromagnetic wave, microwave out, bounces off your car and comes back, and they know from the Doppler shift how fast you're going. There's a beat frequency. When you have two frequencies very close to each other, and then the beat frequency is the hum, doom, dump, which is the difference between the two frequencies. There are standing waves. For example, all musical instruments depend on standing waves. So standing waves on a violin string, standing waves in an organ pipe. These are all standing waves. Earthquake detection, you find earthquakes through waves. There's oil exploration, you use waves to search for oil underground. There's ultrasound in hospitals, for example, making images of things on the inside of your body without having to go inside. Ultrasound also, and of course cell phones. Cell phones can communicate by microwaves. Okay, so all of these things depend upon, for example, the interference of two waves. So a note is a standing wave frequency, and a standing wave results when you have two waves, basically the same frequency, same amplitude, and they're traveling in opposite directions, and on top of each other they form a standing wave. I'll try to describe that. So here's the basics about wave. What a wave does, a wave is anything that oscillates up and down in both space and time. Both space and time. Now that may be a little hard to grasp right away, but there's one fundamental relationship that holds for every wave all the time, and that is the velocity of the wave, the speed with which it goes in meters per second. The velocity of the wave is the frequency of the wave times the wavelength. Now that symbol there is a lambda. It's a lowercase Greek lambda. That's a universal symbol for a wavelength of a wave, and F is the frequency. The frequency in hertz, in other words, cycles per second. So that's the frequency. Now, all waves depend upon the displacement from the equilibrium point for the wave. So we saw, for example, an oscillator, the mass on a spring that went up and down like this. The equilibrium point was where it just sits still. If you displace it from the equilibrium point, for example, you displace it downwards, it'll go up and then it'll oscillate like this. A wave, exactly the same thing. So the displacement, the displacement of the wave from the normal place where there is no wave is called the amplitude. The maximum displacement is called the amplitude, and you can see this wave goes up to the maximum amplitude, it goes down to negative the amplitude, it goes back up again, goes back down again and up again. Between the crests of the wave, that is called one wavelength of the wave, and this is on a scale of distance. So for example, if a wave were going by and you were to take a photograph of it, this is what you would see, okay, in space. And from this point to that point would be the wavelength. Now, on the bottom plot, it's time. Okay, so you're looking at one point on the wave, and you're watching what it does as a function of time. So one point on the wave is going up and down. Again, the amplitude up minus the amplitude down. The time it takes to do one cycle is called the period. So again, with a mass on the spring, you actually measure the period of a mass on a spring, an oscillator. Okay. So that's the time it takes to do one full cycle of the wave, and the inverse of the period is the frequency. Okay, that's how many times it makes a cycle per second. Okay, that's called the frequency. Now, there's a wonderful thing. It's called a wave machine. Here's a photograph. It's a commercial photograph. The physics department has a couple of these, and they're wonderful machines. Actually, the displacement. Well, what it is actually, down the middle there's a spine, a stiff wire, and then attached in the middle are all these metal rods, and they're sort of soldered right on the spine. And the displacement of the wave is when the rods go like this. Okay, it's an angular displacement. Okay, and it's connected to its neighbors because they're all connected to the spine. So if you take the first one here and you angle it down like this, the one behind it will start to move down, and then the one behind that will start to move down, and you'll have a wave gets generated, which then passes all the way down the length here. And you can see what the wavelength is here. Here you can see maximum displacement here, maximum displacement over here. This whole thing is about 3 feet long. So it looks to me like the wavelength of this wave is about 2 feet. Okay? And so also, you know, with a watch, you can actually put a meter stick down here, and you can actually just measure the velocity of the wave too, right? I mean, so the wave machine, the wave goes rather slowly, so you can actually see it go with your eyes. Now, in a regular classroom, we would make these things, okay? I mean, not the commercial kind, but for example, we would take skewers, like shish kebab skewers, and you buy them in the grocery store, and have a duct tape. So this duct tape to the wall, you can see, so rather, you know, nothing fancy here, okay? And then also tied to a post here, and then stretched, and then so you put a skewer every couple of inches, for example, okay? Then, but now now you can take one on the end, you can displace it, okay, twist it, and then the wave will go. And the wave will go very fast, by the way, because these skewers are very light. To slow it down, actually, you put some weights on it. So here's some gummy bears or something like that, okay? And so here, there's some gummy bears have been put on. This is actually another one. It's the same lab, but different group. And then you keep going. You put more on it. You get it's like this. Okay, so now you have these candies or whatever they are, and they're not gummy bears, but there's something you can stick on the end of the skewer. So now, and here's your duct tape down the middle here, and you're ready to go. I mean, this is a wave machine here, and you can see what's down below. Here's Gorilla tape here, which is a very fancy kind of duct tape. It's the right kind to use, and rulers and so on. It's a typical situation here. And you can do this. Now in a classroom with kids, you can do this too, right? Now these skewers are separated by, it looks to me, I'm not sure, about 6 inches or something like that. So they don't have to be close together. They can be far apart. And these things you stick on the end, gummy bears or whatever, candies or whatever, they could be actual other weights. They could, for example, be heavy gauge nails, okay, which you could just tape on. So a nail has a lot of mass, and you put one nail on this side, the same kind of nail on this side. Now you have a high mass, a high so-called moment of inertia. So this wave will travel nice and slowly down here, okay? If you're really brave, you can take two different groups and put them and connect their wave machines together in the middle, okay? And there may be different. These looks like gummy bears. That looks like some other kind of candy. And so maybe one of them could be, for example, heavy with a large moment of inertia. In other words, it could be light. And so now you can start a wave going down the heavy portion of the wave machine, and it'll go slowly. When it gets to the discontinuity between the two different wave machines, it goes into the lighter mass wave machine, travels faster. And then part of the wave gets reflected back in the heavier part. So that's, for example, reflection. Reflection and reflection and transmission at the interface between two different wave media. Now, light does the same thing when it goes from air into glass. That's what all optics actually was. Okay, it's actually exactly the same thing happens in optics as happens in this wave machine, because all waves have all the same properties. So And so now, in fact, you see for a piano or a violin string or a guitar, for example, some of the strings are very thick and heavy, and others are very thin and light. Okay, and the thin and light ones, the velocity of the wave, and therefore the frequency of the note is higher. And for the very massive, heavy strings, the velocity is lower, and the frequency, therefore the note is lower. Okay, and so on. You can also do soft and hard reflections. That's more another issue here. So that's a wave machine, and you can do this in a classroom. And I'm sorry that this semester you're not going to be able to make one of these things, but you can tell. You just look through these, you see this. They're not hard to make. Okay, it's not really hard to make, and it's a nice little project. Well, this happens to be Lake Laverne, and this is a wave in 2 dimensions. Okay, you throw a rock into a lake, a calm lake, and you can see what this wave is like. Looks to me like the wavelength is approximately 1 foot. Crest to crest, it looks like about 1 foot. Okay, and it travels. You can watch it. It travels outward at some particular velocity, right? So the velocity is going to be equal to the wavelength, which looks like to be 1 foot, times the frequency with which it oscillates up and down, by the way, at one point. All right, so now, what are the velocities of waves? Okay, if you take a string, for example, a guitar string, or in fact, as we'll have a rubber band. Okay, I'll show a rubber band later on, but about a guitar string, piano string, the velocity of propagation depends upon how tight you stretch the string. I mean, the wire, the piano wire, shall we say. You stretch it with a tension F. That's a force. So many newtons. Stretch it tight, and then the tension goes up, and so the velocity goes up. The velocity of propagation of the wave down the violin string or down the piano wire goes up by the square root of the tension. In the denominator, there's the mass per unit length. In other words, you either have a high mass wire and this is a mass density, mass per unit length, and so the mass of the wire divided by the length of the wires in the denominator, and the square root of that's the velocity. Okay, that's an expression for the velocity. It's actually a truism throughout physics that the velocity of every displacement, for example, the mass on a spring that we did when we made clocks and measured time, the velocity always goes like the square root of a force term, here in this case the tension, divided by a mass term. Okay, here the mass of the wire divided by its length. So that's a general expression for the velocity of any wave. Now, what about sound waves in air? The velocity is always the wavelength times the frequency. Now, what's true for sound waves in air is the velocity of the wave is always the same. Okay, what changes is the wavelength and the frequency. Okay, but the velocity is always the same in air at standard temperature and pressure. And what's the velocity of sound? Well, it's 1,000 feet per second, actually, 1,000 feet per second. And you know this from, when there's a thunderstorm, and you see the lightning flash, and then you start counting the seconds. If you count 5 seconds, that's when the thunder comes, right? So if the thunder comes after 5 seconds, it means that the sound wave started out 5 seconds earlier, and since it's traveling at 1,000 feet per second, it means that the thunder is 1 mile away from you, because a mile is 5,000 feet. Okay, really 5,280 feet. Okay, but so that's the velocity of sound in air. It's also, by the way, pretty much the same as the velocity of the molecules in the room in which you are at the moment. If you could watch a little molecule in the room in which you are, you would see it. It travels at 1,000 feet per second. It hits another molecule, changes direction, and travels 1,000 feet per second on the average. Some are faster, some are slower, but the average is 1,000 feet per second. So that's about 300 meters per second, by the way. Same thing. So, for example, you could have 300 meters per second. If the wavelength were 1 meter, okay, that would be a 100 hertz sound wave. Okay, if the wavelength were 1 foot, that would be a 1,000 hertz or 1 kilohertz. Okay, which is quite easily heard by the human ear, 1,000 hertz. So, now, look at these are lots and lots of nice sound instruments. I mean, these are mostly sound instruments, actually percussion instruments. All kinds of membranes stretched over something stretched over an area, an open area, and then it'll vibrate. You hit it, it'll vibrate. And here the same thing with these, and these are gourds, I guess, with dried seeds inside, and so on. So these are all sound instruments, okay, just for fun. Now, I'm going to suggest that if you have a smartphone, I hope you do, I'd like you to download an app. It's called the Physics Suite, or better, it's called the Spectrum Analyzer, okay? Now, there are dozens of these, and I hope you can find a good one. The one I use is called Spectrum Analyzer, and I'll demonstrate that here. Physics Suite is good. The Physics Suite actually has about 10 or 12 different measurements. You can measure acceleration, you can measure barometric pressure, okay, the actual pressure of the air in the room, and so on. And you can use it to predict when the weather is going to be good or whether it's going to be bad, because when the barometric pressure goes down, it means that there's wind and storms coming in, and so on. So the Physics Suite has lots of things in it, but the Spectrum Analyzer in the Physics Suite is not as good as the Spectrum Analyzer. So let me try. Let's take a look at this.
Okay, these are some apps. The good for sound spectrum, the best app is Spectrum. It's called Spectrum Analyzer. And another one is called the Physics Suite, or Physics Toolbox and Suite. Let's do the Analyzer, Spectrum Analyzer, because it's much better. So it's called Spectrum Analyzer. There's a pro version you pay for, but if you just close that, here's the regular version. So what do we have here? Well, you can see it's changing, and what it's doing is picking up my voice. So along the bottom is the frequency. So this is 50 hertz, 50 cycles per second. Here's a 100 hertz, 200 hertz, 500 hertz. So human speech is somewhere, 200, 300, 400, and you can see it there. Okay, the top end of human hearing is 20,000 hertz. That's a very high screech. Okay, and if your ears are young and good, you can hear. Most older people can't hear above 10,000 hertz. Okay, now. So the scale is logarithmic. You can see that it's not linear. We can make it linear, and it looks like that. Then all the action we're interested in would take place down here. So by going to a logarithmic scale, it puts the interesting stuff in the middle. So now, I want you to play with this for a while. Just take your time and play with it. Let me try and whistle if I can, and you'll see what the frequency of my whistle is. It's about right there. Now, in fact, let me do that again. So as it's collecting sound, you can stop it here, and then you can read the frequency up here. So let me try that again. I'll stop it in the middle so it freezes. Oops. Again, you have to close the pro. Shoot. Shoot, this is aggravating. Excuse me. Okay, fine. It's not very good. Anyway, here's the peak. The peak is 1669, about 1700 hertz. Okay, that's this peak. So you can read off the peak. Now, so let me tell you. Here's a straw now. Okay, so a straw. This is like a flute. Okay, but so let me do a flute here. Let me blow across the straw. Well, you see there are a lot of peaks here. We'll explain in a while why there are a lot of peaks here. You can also, with your PVC, it makes another flute, by the way. So I'm just going to blow across the top here. Okay, that's the spectrum of the flute. So now, one of the things, if you have a second cell phone, if you go to there's some other downloads. For example, I guess on the physics suite, you can generate any frequency at any hertz you like 400 hertz, and have one smartphone generate the sound and have the other one pick it up. You can check and see. So now I'm going to try to go completely silent, except for breathing here, to see what the noise level is, just the ambient noise level in an ordinary house. About minus 100 dB, okay? dB stands for decibels. So now any noise, for example, let me just tap the table and you'll see what that shows. You see, a sharp tap has a lot of high frequency in it, right? Okay, let me do a low rumble. Okay, those are mostly at low frequency. And the voice has many, many frequencies in it.
And now let's look at this one. This is a homemade guitar.
Okay, there are some rubber bands, some rather stiff and stout, strong rubber bands in your kit for this week, in addition to some straws. So with the rubber bands, you can kind of make a guitar. So what I've done, I have this box actually, and a shoebox might work, but it's not maybe quite as strong. And I've stretched this rubber band around here to make it very stiff. Okay, so it's under a lot of tension. Now watch the frequency when I pluck it. Okay, so here's let me freeze it. Oh shoot. Okay, I've lost some of the tension on here. I want to keep it high tension. Here. Okay, now you see all those repeated peaks? Those are all the different harmonics of this one string. So now, so this is a string guitar. Now, of course, on a piano or a violin or a guitar, you have strings that are much stronger than this one, so you can go up to much higher frequencies here. You can see the highest frequency here is only like 1 kilohertz, 1,000 hertz. So this is a string instrument. And then also we'll demonstrate and then of course the sound instrument is like a flute. Okay, so again you can have a large straw and a small straw, and this will give you higher frequency, and this will give you lower frequency. Okay, and then if we had for example little notches in here, then you would be able to close off close off the flute at certain places. You'd be able to close the end and so on, and you get different frequencies. Now, I wanted to find bigger straws than this, but this is maybe it's okay. Now watch what happens when I do. Let me get the frequency. This is. Okay, the difference of that is I'm closing off one end. Okay, as you close off one end, you change the frequencies, the standing wave frequencies in there. Let me try it with the, actually it's a rather small piece of one of our PVC tube.
Okay, so here's a depiction of what a standing wave on a violin string or a guitar string looks like. We'll get back to sound waves in just a minute here. At the bottom you see that the string, violin string for example, is held fixed at both ends. Okay, it's stretched between two fixed points. So when the string displaces, it flops up and down, and the maximum amplitude is in the middle. So this is, if you look at a full wave is 1/2 up and 1/2 down. Okay, so this is half a wavelength. All right? That's called the first harmonic, and has a certain frequency. This standing wave, actually, the wavelength is actually the length of the string itself. And what it does, it flops up and down like this. The wave flops up and down at a particular frequency, and this point right in the middle doesn't move. It's a fixed point. It's called a node. Okay? Now the next highest frequency up is going to be where the length of the string is three halves of the wavelength, 3 lambda over 2. Now this expression, the velocity is the wavelength times the frequency, is always true. So if you know the length of your violin string here, that'll give you what lambda is, and if you know the tension and the mass of the spring, that's the velocity of the wave, and so that'll give you a specific frequency for that violin string or guitar string. So now you see, if on a guitar, for example, they're frets, and what you do is you hold it down to some point, and basically you change the length of the string that's vibrating. Therefore, you change the wavelength. You change the standing waves that can be set up on that guitar string. Okay, so that's how you get so many notes out of a guitar and out of a violin. Basically, you're changing the length of the string, and then different strings have different tensions. Okay, therefore they have different velocities. So a musical instruments is rather a remarkable thing. Here's a violin hat here, actually, and you can see you can adjust the tension to get to tune the violin to correct frequencies for each violin, for each string, for example. Now again, these things have names, okay? So at the top here, this is called the fundamental, or the first harmonic, and then here's the first overtone of the second harmonic, the second overtone, and the third overtone are called the fourth harmonic. And the frequencies are F0. The F0 is the frequency of the fundamental, or the first harmonic, then 2F0 is the frequency of the second harmonic, and 3F0 the frequency of the third harmonic, and so on. Okay, so they're very precise. Now here's a time-lapsed photograph, actually, of an actual string, rather loose string, by the way, and you can see this looks to me like the second harmonic. There's one full wavelength on the length of the string. Notice there's a node in the middle. It's not perfectly stationary, but it's mostly stationary, and the wave is flopping up and down like this on either side, like that. That's what the wave is doing, and so on. And here's the third harmonic and the fourth harmonic here, or the whatever the names are. It's called the third and the fourth harmonic are here. Now those are standing waves on strings, okay, like maybe the rubber band. Now, what about standing waves in air? Well, the velocity, again, is always, 300 meters per second or 330 meters per second. And so now what we have here are like organ pipes. So, for example, take the one on the left. An organ pipe here has an open end at the top, and it's a closed end at the bottom. So, and it has a length L. That's the organ pipe. Now, what does the molecule do? The molecule that's sitting right up against the closed end, it doesn't move. Okay, it doesn't know where to go. It's just sitting there. So the displacement is 0 there. The molecules at the open end are doing their maximum displacement. Physically, they're going up and down on this figure, okay? And the amplitude is depicted by the red lines here. So the amplitude is maximum at the opening, and the amplitude, or the displacement, is maximum at the opening, and the displacement is 0 at the closed end. So you can see that this standing wave in here looks to me like 1/4 of a wavelength. So in the length L, so the wavelength is equal to 4 times L. So it's a very long wavelength, standing wave here, and a long wavelength means a low frequency. Now suppose you go up to the next harmonic here. Okay, so now you have the standing wave is here. It has 2 nodes, one at the closed end, has another node in the middle, okay, like 2/3 of the way up. Again, the maximum molecular movement is at the open end, and so on. So here, the wavelength is 4L over 3. Okay. Now suppose you have an organ pipe that's open at both ends. Okay, like for example the straw, or the PVC here. Okay, the PVC is open at both ends, right? So it's like this. So it'll have a maximum displacement on both ends and a node in the middle. And the wavelength will be twice the length of the tube. And here, the next harmonic up, again, we'll have 2 nodes in the middle, and the wavelength will equal the length of the tube. Okay, so that's an organ. Okay, but it's also the same here as a flute. So here's a simple flute. Here's a student in 102L a few semesters ago, and you can see you cut the lengths of the straws, graded like this, and you tape them together, and you have a flute. Okay, and if you're skilled, you can actually make this go. All right, and so blowing over the top excites the standing wave. So the standing wave gets excited, it travels down, reflects from the bottom, and goes back again, and reflects back and forth along the length of the straw at a fixed frequency. Okay, and that makes a musical instrument. Okay, so now there's another thing you can do here with, for example, standing waves in air and water, and I left out a word here, in both air and water. It's glasses of water, partially filled glasses of water. So here are, I guess, 5 glasses, pretty much the same. And in the first one, there's no water, and then here there's 1 inch of water, and maybe 2 inches of water, and so on. And so now there are 2 ways. There are 2 ways to excite this. 2 ways to excite this. And we get, I don't know if you can see. Okay, I guess you don't have to see. There are 2 ways to excite this. You can excite a standing wave in the air, in other words, the air above the water, by blowing across the top. Here you have a lot of, the one on the left, far left, you have a lot of organ pipe length, okay, a lot of airspace. So that's a long wavelength, and therefore a low frequency. So you get a low frequency from this end. But at the far right, you have only the wavelength now is forced to be small, to be a standing wave. It has to be small because it only has 1 inch or so here. And so you get a high note or a high frequency note. And you get that by blowing across the top. Well, you know, you can also tap the glass itself with for example, with our ruler here. Okay, our nice steel ruler, you can tap the glass and set up a standing wave in the water. Okay? And on the far right, for example, there's a lot of water length here in this for the standing wave. So the wavelength is long and the frequency is low. You go over to the left-hand side, the wavelength is small, and therefore the frequency is high. Okay, so that's that. So now here's a discussion of that.
Okay, here we have a picture of some glasses filled to different heights with water. This is sometimes called a water glass xylophone, okay, because they give you different frequencies, as we'll demonstrate here. So there's an air volume here, and if you blow air across the top, what you do is you excite sound waves in here. It sends up a standing wave, and this is the lowest frequency standing wave, and the molecules don't move here, and the molecules are moving fast here at the opening. And then if you fill it up with water, there's a shorter distance for setting up standing waves, so the wavelength is shorter and the frequency is higher. As you go from here to here to here, the frequency is higher here. There's a high note here and a low note there. Now, so we have 3 wine glasses here. If we take a look at this, now you may not have 3 wine glasses, but I'll tell you, let me what the heck here. Ordinary glasses will work just as fine, okay? Now, first off, these are not particularly high quality glasses, but in any case, let's see what kind of frequency they ring at by hitting one of them. So let me do this one. Okay, it looks like 939 hertz. 939 hertz. Let's see what this one does, the second one. 972 hertz. And this one? 1001 hertz. Okay, the frequency that lasts the longest is 1001, which is right there. So there's a lot of frequencies here. Now, let's excite this by blowing over the top of it. So I had here's this straw. No, yeah, here's a straw. I wanted a long straw here. Where's the long straw? Okay. Oh boy. Okay, I'll use this straw. It's less convenient, but it's anyway. So I'm just gonna blow across the top of this, just like we're gonna blow across the top of that. Blow across the top of this and see what frequency components there are. Like 680, I think. Okay. And here. 681. And this one, 678. All pretty close, okay? Because they're all the same depth. So that's about 680. So let's fill it up halfway with water. So we're doing this now, so let's do this. Fill it up halfway with water. And so there's about half as much headroom there. 1,050. 1,060. So the frequency is higher here because the wavelength is shorter. The wavelength is forced to be shorter. It can only be half a wavelength or quarter wavelength, can be no longer than this. So the wavelength is shorter, and so therefore the frequency is higher. Okay, so now conversely, so you can set up a standing wave in the air, but if you tap the glass itself, like I will with our metal ruler, it sets up a standing wave in the water. And here in the water, here's a quarter of a wavelength here, and here's the lowest frequency standing wave there can be here. And actually I did draw it right, but let's not worry about that. So this is going to be a low frequency, higher, higher, and yet higher frequencies. So let's do these. I'll do this one will be a little bit. That'll be more. And oops, won't be breaking all of them. There's more. Okay, so let's put them in order here. Okay, so here we go. So there's a long wavelength, low frequency, shorter wavelength, higher frequency, shorter still, very high frequency. So let's see what we've got here. Did you hear that? Low, medium, high. Low, medium, high. Okay. Now I can try, we can get the spectrum analyzer on here and see what we've got. So here, it looks like 759, 880, 966. Okay, so now so now if you had a whole array of cups, glass, wine glasses or whatever with different heights of water, you could actually play a tune here because you could have as many notes as you have glasses of water. So okay, so that's
okay, so I think that here's going to be a little concert here. Concert in 3 notes, I'll call it. But you know, in a classroom now, you can have maybe 15 or 20 glasses, and you could actually adjust the amount of water in each glass to get the frequency you want, and then you can actually play a tune. In other words, you can make a regular music lesson out of this physics lesson. So here goes concert in 3 notes.
Now we're going to have a concert in 3 notes.
Okay. Now actually what you noticed is actually fairly important. What we used there was our handy dandy little piece of wood that we used before, okay, for a couple of different purposes. It turns out this is much, much better than the metal ruler that I was using, okay? I mean, the metal ruler was too sharp, too hard, too many frequency components. But the piece of wood is much, much better, actually. It gives you a much better tone and so on. Okay, so those are standing waves and standing waves in air. So now what are we going to do? Now let me just list the properties. This is maybe a little bit disjoint here, but I want to list all the properties of waves. Now, you may not be unfamiliar with these terms, okay? But some of them you may recognize, okay? And then I'll show some recent scientific results just out of a sense of curiosity and cultural initiative. And then finally we'll end up with the kind of things maybe you want to do. So first off, there's reflection. We know that light waves reflect and sound waves reflect and so on. So when a wave is inside of a medium and when it comes to the end of the medium, for example, the medium stops, okay, it doesn't continue, the wave has to do something. So if it doesn't have anywhere to go forward, it'll reflect and go backwards, okay? Now, then there's refraction. We noticed that a wave actually slows down in a denser medium. And so, for example, light waves, they refract when they go into a piece of glass, a lens. They refract. In other words, they're actually traveling slower inside the glass. And that makes it bend. That makes it change its direction. And that's called refraction. So all of optics depends upon refraction. There's dispersion. The velocity of a wave actually depends upon its frequency, a little bit. Not much, but a little bit. And in other words, it depends on the wavelength. And so that's why a prism will give you a rainbow. It's because white light going in, a bunch of different wavelengths, frequencies I should say, the higher frequencies bend more than the low frequencies do. So you get a spectrum. There's a Doppler. The frequency depends on the velocity of the source or the receiver. So the Doppler has actually been used, for example, I mentioned police Doppler, for example. But, you know, Doppler has been used to actually discover planets on other stars. Okay, these are called extrasolar planets, and also the expansion of the universe was measured by the Doppler shift of sunlight coming from other galaxies. Okay, so that's Doppler. There's resonance. If you have any kind of an oscillator, any kind of a wave, for example, if you tickle it at its own frequency, the amplitude will just get larger and larger. Okay, there's a beat frequency. Sometimes in music you hear a beat frequency. If you have two frequencies very close to each other, put them on top. Standing waves are, of course, what musical instruments are. They're earthquake waves. Earthquake waves are very large, for example, travel through rock. Scattering and oil exploration, quantum tunneling and quantum computers, for example. So in fact, there are a lot of waves inside of yourself, inside the electrical circuits of your smartphone. A lot of electron waves inside of there. There's superposition and interference and also constructive and destructive interference. So those are a lot of words, but I just wanted to say them once. Now, just recently, actually, a new kind of wave was actually observed by humankind. Okay, it's never been done before. They're called gravitational waves. Now, you know, we know about light waves and sound waves, okay? And we know about gravity, okay? The force is m times g, okay, on the surface of the Earth. Mass m, the force on you is mg. Well, gravitational waves, they've been hypothesized since the time of Einstein, actually. And it's believed that gravitational waves would be created, for example, if you had two black holes. Black hole is so massive that even light cannot escape from a black hole, and they maybe have a mass of 1 billion suns or something like that. So you take two black holes that are orbiting around each other, and the gravitational forces are absolutely huge. And then when they collapse and coalesce into one black hole, there's a burst of gravitational waves sent out into the universe. Well, we are a tiny speck in that universe. And by, after 1 million light years or so, that gravitational wave will bathe itself across Earth, planet Earth, where we live. And huge detectors were built to be able to detect those waves. should detect those waves, should they ever arrive. They're both identical. One's in eastern Washington State, and the other one is in Louisiana. I guess Washington State's on the right. The eastern part of Washington State is actually a very high desert, and on the left it looks like Louisiana. Okay, these arms, it's an L-shaped detector. These arms are 4 kilometers long, 4 kilometers in either direction, and they actually send a laser beam down here. It reflects from a mirror and comes back, and another laser beam across here comes back, and inside this little cubicle box, which is where all the fancy stuff is, they look at the interference of these two reflected light waves. And what a gravitational wave should do is should just momentarily, it should change the length of this arm. So this arm has a length you can measure, right? But when the gravitational wave goes by, it does a little dance like this. The other arm in the other direction, 90 degrees, does a dance in the opposite direction. Okay? And they oscillate back and forth. So, they built 2 of them because, you know, if you drop a penny, it'll make these 2 arms change length, all right? I mean, because of the vibration of the ground, okay? If you drop a penny, they're so delicate. A truck 20 miles away that hits a bump, hits a rock on the road, will send these things into jiggling, okay? So the way to beat that kind of background, it's a background thing, is you build 2 of them. And you don't believe anything until both of them do the same thing at the same time. So down below is the displacement. It's the displacement of the wave is measured in strain units, but never mind. On the x-axis, you see there's time in seconds. So it goes from, say, 0.25 seconds to 0.45 seconds. So this whole oscillation starts and stops within 1/5 of a second. And so you see at the Louisiana site in blue, it starts to oscillate more and more and more, then it quenches and stops. At the Washington site, Hanford, Washington, it starts oscillating, gets bigger and bigger, quenches and stops. Let me get myself out of there. Okay? Now, they may not look the same to you, but they are the same. I mean, apart from the fluctuations in the measurements and so on. So those are 2 waves. They're actually gravitational waves. So if you compare the 2, you put them on top of each other, well, you know, they start going up and down at the same time and stop at the same time. So you can do various data analyses, and that's the stuff on the bottom here. And also the Europeans built another smaller one called the Virgo Detector, and theirs basically did the same thing, but didn't, as you can tell, the Virgo Detector did not have quite the sensitivity. I mean, let me put it this way. The U.S. group has been building this detector, the so-called LIGO detector, well, for about 40 years or longer. And it's a great scientific achievement. And the Europeans only started a few years ago, so it's not surprising that they don't have the sensitivity yet. So that's a very exotic wave, okay, but yet a wave. Okay, so the last, here's the last slide here. What to do, okay? Well, I would first off download the spectrum wave analyzer or the physics suite, some way to measure in the same way, and you may have to download several things and test and see. Okay, and then just play with it. I mean, whistle, talk at it, make some sound, and see what the frequencies are. Okay, and then you can excite set up standing waves in straws or the PVC tube you have. Make a rubber band guitar. In fact, I only stretched one rubber band across here, but I could have stretched. I have 3 of them. I guess I could have stretched all 3. And then you could have played a 3-string guitar here, okay, by having each one have a slightly different tension. The box here, by the way, is called a sound box, and so you amplify the sound much more, just like a guitar has a sound box and a violin has a sound box. So that's the reason why having a big box like a shoe box or something is a good idea. Then with 3 or 4 or 5 glasses partially filled, try to make a tune. Okay, see if you can actually make a simple tune. And then make a musical instrument. And I would say that the last one here, try to do something so that your children someday can also do something. And finally, just let me say, if you just go to a web browser and you do a do-it-yourself, DIY, do-it-yourself musical instruments, you'll get a huge number of things, absolutely huge. Some of them are very good, very clever, very wonderful, and some of them are, not. You'll quickly figure out the ones you like and the ones you don't like. So that's it, and I'll be here at the same Zoom address tomorrow, 3:20. Tomorrow, which is Monday, Monday at 3:20 in the afternoon. Anybody want to make any suggestions or any questions about this? I'll see you then. Thank you. Bye.